So thanks the organizer for giving me the opportunity to give a talk. And so now I'm going to talk about some specific a specific system of HCN masers in carbon-rich AGB stars. And so I would first like to start with the dichotomy of circumstellar chemistry. So we have oxygen-rich and carbon-rich stars. For oxygen-rich stars, most abundant molecules besides CO are SiO, H2O, and OH. And this molecule also have a lot of major emissions in oxygen-rich star, and these are one of the important tools in parallax measurement that gives the distance measurements of oxygen-rich star. However, for carbon-rich star, they do not have these strong masers in many of these molecules. But on the other hand, it contains a lot of the circumstellar envelope contains a lot of carbon-bearing species such as HCN, CN, and acetylene. And so this HCN molecules has a large number of energy levels. Also have some low-lying vibrational states that could lead to many thermal and also maser emission. And however, not a lot of attention has been paid to HCN maser, and so this is the topic that I'm going to talk about in this talk. And so due to the high abundance of HCN in carbon-rich outflows, it actually has a significant role in the cooling or in the energy balance of the circumstellar envelope, in particular in the parts of it where CO is optically thick. And also, as we can see in this example, CO emission in the ground state is spatially extended, so it serves as a good probe of the physical conditions in the circumstellar envelope, and also as we will see later in some of the results, it emits in multiple energy states, including the ground state and also excited vibrational states. So this the large spread of energy levels allows us to derive the physical properties through excitation analysis or radiative transfer modeling. So exchange is also is important not only in carbon-rich stars, also important in oxygen-rich stars. It's an indication of non-equilibrium processes. So let's talk about the molecular spectroscopy of this molecule. It has three main modes of vibration: the CN stretching and bending mode, and also the HC stretching mode. And I'm listing here some of the more important vibrational states in this presentation. So besides ground state, the lowest two vibrational excited states are all in the bending mode, and they correspond to the energy level of about 1000 Kelvin and 2000 Kelvin. And these are very accessible energy in the context of the AGB winds, and so that leads to many thermally excited transitions in these two energy states. And then later I will talk about a specific system that concerns these two high-lying energy states, that is 4000 Kelvin above the ground level. Recently, Manali Jasti has conducted an APEX survey on a large number of carbon-rich stars, and also with many spectral setup covering many possible HCN transitions, and she discovered numerous thermal and maser emission lines in carbon-rich stars in the vibrational excited state. And all these vibrational states have also been detected in AGB stars of other chemical type, like in S-type star, as recently reported by the Atomium Consortium, that we have detected the vibrationally excited HCN lines up to V2 equals 3 in some S-type stars, and it has also been detected in individual oxygen-rich objects, as shown in the example spectrum here. Yeah, so besides thermal emission, there are also many masers from HCN molecules in carbon-rich stars. The first discoveries are all around the V2 excited state, including the V2 scope 1, V2 scope 2, and also there's a very peculiar ground state HCN maser in several sources. And if you go higher, so there are also the detection of V2 equals 3 maser in one of the sources from the APEX survey that I have just mentioned about. So in total, Marlene just has discovered 29 new masers from 13 carbon-rich stars. Most of them are in this V2 equals 1 level, and also this is consistent with other historical searches. And next, so above the V2 equals 3 state, the next highest level is the next energy level is V2 equals 4, but at this level there are many vibrational is the bandhead, correspond to the bandhead of many vibrational states, one of which is this 110 if we order the vibrational quantum numbers in this way. And there's a very special phenomenon of because these two energy, the rotational energy ladders of these two vibrational states are so close to each other, and the rotation and vibration Hamiltonians of the two of the molecule interact with each other, and this effect is known as Coriolis mixing. And the consequences are that the transition probability as well as the energy levels around the interacting regions would be severely perturbed. And quantum mechanical computations has suggested that the perturbation was the most prominent near J equals 10 of these two transitions. And this is expected, so it's predicted that the 891 gigahertz transition would exhibit intense emission in the far infrared region, and so some of people call them laser emission, and in this talk I will refer them as maser emission, but they are essentially the same thing. And also another besides 891 gigahertz, another transition at 805 gigahertz also predicted to exhibit maser emission. And in this system of transitions, 3 of the lines are observable with ALMA in band 10. And so astronomically, this system has been observed in several carbon stars in early 2000, and we have seen that the emission, the intensity of the line of at 891, the cross ladder transition is much higher than the pure rotational transition at 805 gigahertz. And so in cycle 6, we have an ALMA proposal in order to carry out more searches of more of these examples of HCN masers, and also trying to obtain some constraints on the spatial distribution of these masers. And in the end, there have been 6 setups that were observed, and all of them have shown intense HCN maser emission. So the detection rate was 100% in this sense. And we also confirmed the previous observation that 891 gigahertz maser is already stronger than the 800, the corresponding line, the 805 gigahertz line in the same source. And then in cycle 10, we wanted to also follow up with an ACES survey, also to cover this 894 gigahertz transition that was that has never been observed or detected before. However, because of a number of technical difficulties, especially the difficulty to find a strong enough quasar as a bandpass calibrator, the completion rate has been hopelessly low at the moment, and there has been no data delivery yet. And besides ALMA observations, there has also been some Herschel projects in the archive, and also in 2018 we have submitted a severe proposal to follow up to obtain an extra epoch in order to assess the variability of the HCN emission. So there are several projects, and most of the projects by Shanishaju are targeted observations, specifically focusing on the system of 6 transitions, as indicated here, towards a sample of 7 carbon stars. And besides the targeted observations, there are also some spectral scan observations that the postdoc at Nanjing University, Wenjin Yang, is currently analyzing the data. So far, according to her the draft paper, we have detected these 3 major emissions from all the targets, and we also obtain high detection rates of the other 2 transitions. 966 is and 1055 gigahertz are all both the purely rotational transitions on this 110 ladder, and the 894 gigahertz has not been detected in any of the surveyed targets. And another another important observation is that the intensity of the 891 gigahertz is always much stronger than that of the 964 gigahertz. So we suppose that it will lead to an overpopulation of the J equals 9 level, and hence there should not be population inversion for the 10 to 9 transition. So this explains why there's no detection of the 894, and because the intensity of the 809, the cross ladder transition is so strong to the J equals 9, there is a population inversion for this transition, and also because of the relative intensity, 891 is stronger than 964. It also leads to population inversion of this transition, and subsequently also on the transition of in the higher 12 to 11 rotational transition, and this explains the also high detection rate of the other 2 lines. Yeah, and then going back to the ALMA data, because the detected HCN emission is so strong, we are able to do self-calibration to improve the dynamic range, and the numbers are all very similar to in different sources in most of the sources. The initial dynamic range using phase referencing calibration was about 100, and after self-calibration on the MESA, we obtained a maximum dynamic range of about 3,000. But for other setups where the detection was weaker, then we were not able to reach as high a dynamic range as 3,000. And so this is the one that I showed was 805 gigahertz, and this is 891 gigahertz, and we also see similar results. And if we yes. So as Yoshiharu Asaki has talked about it on Tuesday, there has been a high-frequency long baseline campaign making use of the HN MESA as a tool to verify the band-to-band calibration of ALMA. So they have compared the quality of band-to-band calibration as well as self-calibration. And after self-calibration, we have we have spatially resolved the emission from the 891 gigahertz MESAs, and we see that the MESA is clearly spatially resolved, and also it the emission forms a ring around the star. And if you look And if you go through the channel maps in detail, we also see that on the surface of the star, along the line of sight towards the surface of the star, we see weaker emission or in fact absorption against the background continuum. And so this is the high frequency campaign in 2021. And combining with my data in 2018, we see also variability in both the intensity and the line profile of the emission line. And I'm here showing a very similar example for another object, Hydra at 805 gigahertz. We also see the improvement of the in the dynamic range, but because the emission here is weaker, so the improvement is not as good. And we also have a similar for 891 gigahertz. And because the ALMA observation in band 10 uses the double sideband, it has the instantaneous bandwidth of 15 gigahertz. And so we simultaneously also cover many of the other HCN transitions in different vibrational states. And most of them are firmly excited, except perhaps maybe for some of the L-type doubling components of the V2 state in isolated sources, but most of these are firmly excited emissions, except for the V2, the last two sources. And we can see a gradient in the extent of the emission and also in the intensity. So the entire data set will eventually allow us to carry out excitation analysis to derive the physical condition in the envelope. So HCN for the carbon-rich star would be as useful as SIO in oxygen-rich stars. And so I'm leaving my summary slide here. So we have measured, we have detected a large number of HCN masers with different instruments, including ALMA, Herschel, and Sophia. And we have obtained spatially resolved image of 891 gigahertz maser, which is always stronger than the 805 gigahertz maser, and also another cross-ladder transition at 964. And actually, this behavior is consistent with the theoretical calculations in quantum mechanics. And it also explains why we, in the system of the Coriolis mixing, we only detect 5 out of 6 transitions. And I think that's all. Thank you.
How high are the brightness temperatures?
I think it depends on the source, but for IOC 1016, I think it's up to 10 to the 8, so 100 million Kelvin.
Is there any carbon-rich star where you have searched for these HCN masses, but you don't observe it? I mean, in other words, are they present everywhere in carbon-rich stars?
Yeah, it's so at least for 805 and 891 gigahertz, the detection rate is 100%.
100%.
So, yeah.
Okay.
But in Herschel, I think there are some special scans also for carbon-rich planetary nebula, like CRL2688, and I think I've done a quick look on that, and there's no detection, and these are really only in AGB stars.
Okay, and in any S-type star?
I think in the Herschel database, so we don't have ALMA data on S-type star.
Yeah, okay.
In Herschel, there are no detection on S-type star as well as oxygen-rich or supergiants.
Yeah.
It's exclusively towards carbon-rich AGBs.
Okay, thank you. So well, one question by Taisa.
Sorry, Kata. Thanks for the nice talk. With the variability of the masers, does that follow the phase of the pulsations, or?
Yeah, Wenjin is now analyzing, but the first result is that they don't. So we have some measurements that are at the same phase, but at different cycles, and they are very different. So there's no apparent variation in phase with the linear, infrared, or optical.